All right, so this first lecture we're going to be talking about alternative number systems, which is the best way that I could think to describe it for first-year students. We're talking about radices. I'll explain exactly what those are in a short while, but by the end of this lecture, you're going to understand how 10 plus 10 can equal 100, 4 plus 4 can equal 10, and 7 plus 3 can equal the letter A. So we're going to dive straight into it. We're going to be talking about what a radix is, what binary is, why we use it, and how. We're then going to talk about octal and hexadecimal, what their purpose is, before we get into change of base, which is going to be a series of techniques for converting between different radices. And then tomorrow we're going to talk about binary arithmetic. We're going to talk about addition, subtraction, and multiplication to show how the process is indeed the same as what you would do with a base 2 number system, or a base 10 number system. But I also want to put focus on complements and bit shifting, which is something a bit more unique to discussing binary and plays an important role in computer science as a whole. So getting into it, what is a radix? A radix is a base for a system of numbers in the shortest possible definition. So we're used to the decimal system, which is base 10. So each digit has 10 possible values. For a given radix, we'll call that x, and a number of digits, which we'll call n, the number of possible values per digit is x. So if you have a base 10 system, there's 10 possible values per digit. If you have a base 16 system, there are 16 values per digit. And the possible values per n digits is x to the n. So if you have a 4-digit system, or rather a 4-digit number, if you have a 4-digit number, then that number is in base 10, then there are 10 to the 4, or 10,000 possible values that number can represent. Now, there are names for many of these number systems, which is what we're going to be using for this course. So octal, hexadecimal, decimal, binary. But in general, we write our radices as base x. So decimal is base 10, binary is base 2, octal is base 8, and hexadecimal is base 16. On to what binary is. Simply put, it's ones and zeros. This represents physical electrical signals in transistors, which are teeny tiny computer components. They are effectively switches. So you have millions upon millions upon millions of these switches in an average CPU, and they are atoms wide. They are extremely, extremely microscopically tiny. But the 1 and 0 binary digits map to on, off, true, false, yes, no, up, down, whatever you want to think of it as. This is a binary number system that we are using, so it's 2 possible values. And again, it maps to the physical electrical signals that are sent and received by transistors. And it also maps to machine code, which is the most bottom-level code that a computer reads. When you take your computer architecture class, you're going to see machine code instructions, and those instructions are going to be written in binary. On to how to read and write binary. So we have 1 binary digit is a bit, 4 is a nibble, and 8 is a byte. A binary string of any number of digits is going to be called a word. And generally speaking, when we write binary, we group it into 4-digit groups. We group it into nibbles. This comes in handy later on when we start talking about change of base. When you do your assignments, when you're doing change of base, I want you to group your binary digits into sets of 4, and any leading sets that do not contain 4 digits, I want you to pad them out to the left. So you'll see in later lectures where I show how to do these conversions, how I want you to pad these out. But just understand this basic terminology. And now we'll move on to the metric system of binary. So we can use this measure with bits or bytes, bits being a lowercase b and bytes being an uppercase b. So these two are used in different applications. Binary or bits are used in data transfer to measure speed. So say something might be downloading at 10 megabytes or megabits per second, or something might be uploading at 1 megabit per second. That is how we measure data transfer speeds across networks. On the other hand, storage is generally shown in bytes. And regardless of which one you're using, the metric units are going to be the same. So instead of a base 1000 prefix system, we're using a base 2 to the 10th power prefix system. So instead of 1 kilobyte being a 1,000 bytes, 1 kilobyte is 1,024 or 2 to the 10th power bytes. Same thing with a megabyte. That's 1,024 kilobytes. 1 gigabyte is 1,024 megabytes. 1 terabyte is 1,024 gigabytes. And if we multiply all of these together, we get that 1 terabyte is equal to 1,099,511,627,776 total bytes. Now, think about how much stuff is stored on your computer's main drive, whether it be a hard drive, solid state, M.2, whatever. Usually these are 1 to maybe upwards of 4 terabytes. And now think about just how massive of a number that is and how much data, all in binary, is flooding in and out of your hard drive or your solid state in such a short period of time. Next, let's talk about octal and hexadecimal. For simplicity, going forward, we'll refer to hexadecimal as hex. So octal, most of the time you'll see it being used for educational purposes to show how it maps evenly to 3 binary digits, but you do see it in applications such as assigning permissions to Linux and Unix users to the chmod command. I am not aware of any other applications for it, but I'm sure they are out there. Hexadecimal, on the other hand, which 1 hexadecimal digit maps pretty evenly and nicely to 4 binary digits, or 1 nibble. Notice how that makes things very easy to read. This has myriad applications since it provides a really nice, easy way to read binary, which can get extremely long in a short period of time. But we see it used for color codes in web development and digital art. You'll see it come up in game design. You'll see it come up in cybersecurity for things like encryption keys. You'll also see it being used for hash codes and many, many, many other things. Again, it's all binary at the end of the day, but we use hex in these cases to make it easier for humans to read. And so with that, we get into change of base and the techniques to do that. So you'll see that in the upcoming lectures. There are 5 separate lectures all talking about this. Each of them is really short, under 5 minutes long, intended to be really nice and digestible for you. So stay tuned for those.